Okay, hey,
I got you.
Justin, get away from the microphone. You lost privileges. No more activity room for you. You go to your board.
Mark. If you go back,
You go to your paper and draw there.
that one is gonna be
Negative
Is it
one.
more? Negative two.
Is it war?
It's a Band-Aid.
It's a butterfly.
It's a Band-Aid.
That sounds like a square.
But not three.
No.
Because there's a
Get
square.
sticky out of your ears and everything.
Alright, Justin, go sit. You don't get
Because
more.
negative 3 and 9 would just be like.
Now it's
Joseph.
Doesn't look like butterfly legs.
Kind of.
This goes back there.
Sit
Sit it, James. Sit it. Okay, hey,
Sydney,
take a seat. Take a seat.
throw the
Okay.
black one back. I need.
Alright, now the reason why I bring this up, Justin, go sit.
I'm trying to put the markers away.
Okay, in fact, I'm gonna leave that working. Alright, the reason why I brought this up.
Like my.
The next time we're going into exponential squares, things with powers. We were just exiting the part about linear equations. Okay, you need to be able to find slope, find equations of lines, and be able to prove things. Now, it's great that you guys use slope and figure it out. Most people can kind of guess numbers that will make it work. Or at least you can like look at the graph and go, okay, it's got to be in this ballpark around the 4 range, or negative 2, 4. But checking why it works is the hard part. Okay, because we have that curve, we have this parabola, because we have the equation for it. So you know what numbers you can plug in for x and what the y is going to come out to be. So that's kind of be where we're going to check. To find the slope, you got to use that 0, 2, and make sure that when you're doing this, now I know a lot of people just they just count with their fingers, which is fine, but on a test, I want to see that you're subtracting the y number, you're subtracting the x numbers, and when you actually subtract those, you're getting 1, negative 1. So that means it's negative slope, so it's going down and to the left, or down to the right, or up to the left, that type of thing, depending on how you look at this. And once you have that, then you can set up your equations. Now, the reason why I can immediately write down my equation of my line, because they gave me my y-intercept. That was one of the things that they just gave me. I know I think some of you said yesterday when you had the problems about linear equations, I think one of the questions just gave you that y-intercept automatically. That's nice that you have that. Now that we know that, what's got to have happen here is that both of these equations, I have that exponential equation, which is a parabola. I have the linear equations. They have to give me the same y number out of that thing. So to get the same y numbers, just set them equal to each other. Because at some point, this has to have happened. That has to happen. So once you have this, you can solve for the quadratic. Move the 1x over, subtract the 2 over, and now you can go ahead and start factoring. Those are little things like why we did factoring in Algebra 2. It was to find solutions for quadratics, and this is the actual application of it when you have intersections of different objects. Now, obviously, the new object today is the actual quadratic.
Right.
But being able to do this should be pretty straightforward. So this should be, x minus 1, x plus 2, and the two answers here should be positive 1 and what, negative 2? Yeah. And obviously we already have the positive 1, that's already taken care of right here. That's the x number that makes it work. We already know 1 and 1 worked. It works in both equations. But this should be the other one, and so plugging in negative 2 gives you 4 on that quadratic, and it gives you 4 in the linear equation when you plug in negative 2 into it. Because negative 2 squared is 4. Or if I plug negative 2 in here, negative 2 times negative 1 is 2, and that 2 is 4. So it gives you the same answers both ways. Okay, this is something that, I give it as a challenge. It's easy. Most people can figure out by, using hands and stuff and just counting. But showing work is a completely different story. I don't expect to see detailed proofs and other things like that. But I do want to see stuff that we use, that we've learned, and try to apply it. Now I know, that's throwing in the deep end day 1, kind of going through it, but that should be easy enough that we should be able to do it in the long run. Make sense? These are things we're going to be doing more and more. And to throw at problems, try to lead from old stuff to new stuff every now and then, give you a challenge, see if you can figure it out. You guys figure it out quick. It only took you a minute or so to figure that out. But these are the things, it's nice to see why there's tie-ins and other things like that. Okay, today we have a couple new things, so I'm really impressed, happy with that solution here. What we have to do today, we have to talk about exponentials today. review it. I'm gonna do that for maybe 10 minutes or so. I have a couple of problems I'll put up here on the board, we'll try it out. And then the new thing that we're gonna be doing here is talking about concavity. That's brand new. I don't think we've talked about concavity
Yes,
yet.
we have.
So,
Like in your
have
teeth?
you done it? Okay. Good. All right. So, let's walk through a couple of problems. So number one thing, exponential form. You know, this is quadratic. You know, a function with the power. What I'm talking about is that, you know, that does have a curve to it. You see it right there in front of you. But what I'm talking about is what happens when we switch it around. And you put the x in the power. It will grow, it just won't go past the y-axis too far. It's not going to bow up on the other side. The graph, the difference between these is the major part of the graph. It's going to look like this. What I want you to see today is how can you tell the difference between if it's a linear function or if it truly is an exponential. I want you to see this in front of you to see how you can tell. So, here's one of the things I want you to write down. Okay, this is going to be my first example, then I'll show you a second example here in a minute. Okay? Alright. Y equals 2x plus 3. Write that down somewhere in your notes. We're going to make a little table, and I'm going to show you this little shortcut that I use to figure out is my problem exponential or is it linear? By just looking at the data without having to look at a graph. So if I had a function, I can figure it out, obviously, if I'm looking at the function.
It's called that.
But, okay, so, x's and y's. So if I plug in a couple x's, 1, 2, and 3, I only need a couple points of interest.
That's a few.
Okay? So, if we plug in the number 1 here, now we already know this is linear, but I'm going to show you using data. So if we plug in the number 1, 2 times 1 is 2, plus 3 is 5. Plug in a 2, 2 times 2 is 4, plus 3 is 7. 3 times 2 is 6, plus 3 is 9. You can look at the data and actually see that it's linear. Because the slope going from here to here is being the exact same. It's using the same pattern. This side's going up by 1s, this side's going up by 2s.
How did you?
It's linear.
How did you choose to say data instead of data?
I just either one. So, alright. Now,
How much data do you have in mind?
how much? Alright. So, on this problem, it's definitely linear. There's a pattern that you can recognize that it's going up by the same numbers every single time. That makes it linear. Now, how if I know if it's exponential? So let me give you an example of that. I have one right here.
Where's your Chrome pad?
It'd be multiplied every time.
Underneath my books.
And you're right. Now let me look. Okay, or let me show you here. This data set. Just write down like the first 3 numbers. We're going to figure out if this is truly exponential or not, just using a random set of data that I pulled out of your book. Okay, data.
No, I think
Can you just say like that? It makes me so much more
as
happy.
the numbers,
Adjacent to the sack.
as the numbers x side increase.
Write down like the first 3. Okay, write down the first 3 numbers. Now, what I'd like you to do, if you have calculators, which you should have, at least a couple of you in here, I want you to subtract these numbers from each other. I want to see if it's going up by the same number. Because that's going to check, is it linear? Because I already know the years on the one side's going up by 1.
It's not.
It is.
I can see it.
They're going up by 0.5 each time, approximately.
10.
What?
Okay, I want to know what it's going up by.
About 500,000 each time.
Subtract down.
Oh, I thought you were saying 0.005, that's why I was confused.
Okay, it's going up by 7.
Okay, just subtract the first 2 numbers from me there, Justin, because I know you got it.
Oh, I was doing, you said
57.
subtract all the way
Oh,
down.
57.
No, just subtract the top 2.
Oh, well, right the first
0.5
5 is
by
negative 43 million.
No.
Oh.
I don't want the millions. I just want the one that's decimals, just subtract them.
Oh.
Say it.
So negative 43.
0.437 in difference. Okay, it's going up actually, it's going up. Okay, next one.
Wait,
0.437. What?
What?
Is it?
Oh,
No.
437? No.
even the first one, is that even,
It does
It's,
not. 437.
is the first one 0.437?
457.
Oh, yeah, it is.
Because it goes to 9 and then plus 3 is
Like that?
3.
Okay, so are they going up by the same number every time?
No.
Not
Not
linear.
even
Not
2.
linear.
No, you
No, wait, 0.337, I thought.
Sure.
Wait,
Try it,
0.337?
Okay, right there, I can already stop, it's not linear. If you're actually subtracting and you found that there's a difference in numbers, even though I'm going up by ones on the
Are you
left,
sure that's yours?
and suddenly the differences change, it's not linear anymore. So it's gotta be some type of
I
curve.
got negative 74.
Ooh.
I stole it.
I don't know what you're doing.
Okay, no, I'm not stealing it.
Alright, now, to show if it truly is exponential, what I'd like you to do is I want you to divide, take the top number, or I should say the bigger number, because it's going up, so this is a growth problem. I want you to take the 13.29 and divide by the number that was below it. So I guess on the graph it'd be the number above it technically, but I want to take 13.29, 0,
0.034.
and we're dividing by 12.853. Okay, like that. What do we get?
1.5339.
339. Okay. What this is, that's a growth. It's a product. It's a growth. We divided, that's what they multiplied on the 12.853 to get the 13.29. I want you to do the next number now.
What?
Take the next number, take the 13.747, the next rung, and divide by the 13.29.
1.034.
Say it again?
It's almost the same.
1.034.
Okay. It's nearly identical.
But not.
But
It's
no.
close. It's close. Okay?
Not.
What's happening here is that if the numbers are insanely close like that, it's probably showing you that it's some type of exponential growth or some type of square term or cube
Even
term
if they're just off.
that's happening. Yeah, if it's off by 100th or 1,000th, it could be something where if you keep going, you'll notice the pattern's almost the same. Okay? This has potential to be an exponential growth problem. This number that you're seeing right here is the actual growth. So what I mean by that is exponential form problems that we talked about in pre-calc. Now if you think all the way back to what we did, this was the type of problem that we discussed. That was an exponential growth problem using E, the natural
Yeah, we did
number.
the P one.
Okay.
What was the P, the principal?
Yeah, the principal, A, to the T.
And the ERT.
Yeah, that was the one we were talking about. And this is the total, so this is the amount you're having. This is probably the formula they're using. So they have some principal amount. This principal amount is the initial amount you're starting with. That's the 12.853. The A number is that growth number. If the number stays the same or really close to being the same the whole time, that's the number they're exponentially growing by. The T is how many times they're going to multiply it. Because how this works is every time you go up, you multiply by the same digit. And then the amount is what you're turning into. So if I know that I'm going to go to the, if this is my starting run, shh, hey, let's get rid of the computers.
Yep.
So if you start with that 2003, and we're getting 12.853, and we know eventually we're going to end up at 2,000 or at I shouldn't say 20,000, but in 2008 we're going to end up at 15.234. What should happen here if we're solving for t? This number should be the difference between when you started to when you ended. That's how you know if it's also growing. That's another check. Because I know a lot of you are like, well, the number isn't exactly the same. You could do it this way. Plug in the first number, figure out roughly what the growth is from the graph. Use a data set down the road. And this t number should be the difference between 2003 and 2008, which should be 5. This number should be 5 if we solve that correctly using logarithms. That's another way to check. But again, that's assuming that the 1.034 is the correct number. We can actually find that amount if you type in this number here, the 12.853, the 15, leave this number as A, and just type in the difference in years, like 5 years. And we can figure out this number too. But I think the easiest way to do is just divide. Dividing is that number you're going to figure out. This is different ways to look at exponential problems, to figure out if they are exponential, how to figure out what the next numbers are down the road.
Is this a population curve?
Really?
Yeah, Gardner has
Yeah.
No, Garner
Well,
has 15.757.
Okay. All right. Hey, let's move on here. Okay.
Miss it.
Okay, so that's our intro on exponentials. This trick right here is something you need to know right now. You need to have that written down somewhere in your notes. I'm gonna leave that up there.
Okay.
Because we're gonna
I
use
feel like
that.
we would have done
Just
it
wrote it
last
down
year.
on my.
Yeah, we did work on it last year, but the approach here, what I did in the beginning was different. Like dividing the numbers to figure out what they're growing by.
Yeah, so you're
Instead of
teaching us
doing
different
large.
things.
Right?
Yep, different
You're
structures.
contradicting yourself.
Why do you call people who are
Why
dumb
T?
dense?
Let's stay
They
to
got
that.
a thick skull.
Alright,
I was thinking about populations because, you know,
Their
Density,
skull.
Alaska?
population density.
yeah, Alaska is not
India is a
dense.
very dense place.
Yeah, but Alaska's not dense. But I feel like
hey, let's focus. I don't want to have any conversations right now. We gotta get through all this stuff. Alright, next part. Okay, now we're gonna talk about, is now we know exponentials and growth and decay, and hopefully we have that formula written down.
Okay,
Following
just hold
the-
up here.
Okay?
It's A equals half.
This is something we're gonna practice tomorrow, is finding these numbers, these growth, or figuring out the years. We're gonna look at how to type it in your calculator again if you have one. That's something that's gonna be a part of the homework, is figure out, the number of years that'll take you to grow, or to what they say, to mature to that number.
Okay, go ahead.
Okay, concavity is our last example today. Concavity is looking at whether a function is bowing upwards or downwards, depending on your sets, your points. Okay, in fact, I'm just gonna draw one here, okay? This graph is concave up. It's concave up, because it's going upwards, right? It's common sense. Even though the function, so if I had a graph here, maybe the graph is actually, as you go left to right here, even though the function is going down on this side, it's decreasing in value until it gets to some point down here where it hits that zenith point.
What is the zenith point?
It's that either lowest or highest point, so it's a min or max type of thing.
Isn't zenith
So-
the brand for something?
Yeah.
Let's focus on this stuff. Okay, even though this graph is decreasing on this side, it is still concave up. Because if you were to look at just a portion of it, the bowl is upwards. So if you were to turn the paper a little bit and it were to hold water, that's usually concave up. That's how I think of it. Okay, this side, even though it's increasing still, it is also concave up. That's still concave up because it still can hold water because it's bowing upwards.
What good is a bowl that doesn't hold anything?
To strain.
Hey, okay.
Let's stop. I'm getting annoyed. Okay. All right. Let's move on to the actual graph where we're going to see that you can change the words. It can be decreasing but be concave down. It can be increasing, concave up or down. So I want to show you this graph of what I'm talking about. This is something we're going to start applying to all of our graphs, especially data sets for exponentials. And so I'm trying to introduce you to these functions here. Let's see, what does it deal with? Nope,
that's not it.
that's close. Is there three here? What is the deal? Sidebar. There we go. I don't know why it's not showing. Okay. So, this graph next. Let's get rid of the sidebar. Okay, this graph has parts where it's concave down, it's concave up, but the function itself is increasing and decreasing at different moments. And how you can tell, there's an interval from one letter to the next letter, it can automatically change. So like for instance, at A to B, from A to B,
Concave down.
it is concave down.
But it's
Even though the
increasing,
function
oh my.
is increasing, it's still concave down. Because it is bowing downwards. The bowl, it'll dump out stuff. So it's increasing, but it's concave down. Now, why I'm bringing this up, this topic. We are going to do checks in the middle of this year because one of the things we need to focus on in calc is rate of change, slope. There is a formula that we have in calculus that you can do over a function. Let's say you have some mathematical function formula that they have for this picture. There's this little trick we do, it's called a derivative, that you do to this function, and it will tell you if it's concave up or down automatically, without having to look at the picture. you can look at the formula and figure it out. And even though it may switch up and down, right and left, right? You can tell by the function itself where it's gonna do it. And so it's kind of clever the way that that works. Like one of the things we started with in pre-calc is knowing whether the tails are up or down the right and left side. We talked about the end behaviors. We talked about how to graph functions, how many times it's gonna change positions, how many times it has potential to oscillate up and down. So that's one of the things. So the new thing that we're talking about this year is concave up and down. Now you guys said you kind of recognize it, that's great. But recognizing it all the time. So going from B to C, it's decreasing from B to C, but it's concave down still. C to D, it's concave up, even though it's still decreasing. The reason why there's a big difference here, even though it looks like it's the same line, this was bowing downwards, this one's bowing upwards. So it changed from concave down to concave up in one letter. This one's concave up. Then from E up to F, it's concave down. F, it's going down to G, that's concave down. Now it's going up from G to H. And then it's concave up from H to I. The function itself is increasing and decreasing all the time, but you need to recognize when it's bowing upwards or downwards. It's really hard in the middle, because it will just flip at one letter. That's one of the things we're going to be looking at this year. I thought this is a good way to do this, because we're already talking about exponential, we're talking about curves. Now we got to start talking about the little pieces of curves. So like the parts of it, because it is important. Okay, questions with concavity at all?
No.
Okay, now obviously today is the intro day. Tell you the words, show you pictures. Tomorrow we'll put it more in practice. Okay, all right, your homework. You have the rest of the time today to work. I know you don't have a lot of time. You have about 10 minutes or so to kind of work on your homework, even if you got it done or not. Homework,
I got it.
page 7, if you were working on it
I was gonna
yesterday.
say, did you really?
Page 7 is due on Friday.
Nicole said
I'm doing a book check today, if I didn't do it yesterday, because today is the book check day. So I'm checking to see if everyone had their book cover.
Jen, did you get your book covered on?
You don't have a cover on, do I have to go and get my book?
I had it on yesterday.
I checked all of it. You guys,
11 pages.
I don't know if somebody.
Yeah.
13 and. Go ahead.
Did you do the homework? No, I asked did you?
Oh, no.
Here's your
Come on.
You need to be parallel.
You know me a little better, guy.
So to be
Well, you're
parallel, you have to use the same
adulting.
slope as the house. But
You
yeah.
caught the end of this
So what I would
video.
do, I would do.
You just made the end of the
Point
video.
slope. The point that they're giving you is 1.5.
Hi, Ward.
Use the slope that they gave you yesterday. So rearrange the ones.
I made this during your class today.
Then write it for parallel. Parallel, use the same slope, but you have to use the new coordinate. Perpendicular, you flip the slope, make a negative. That's all it is. So the equation for
You can watch it. I still, you know, I'm still gonna get through this class. I just
say your slope.
haven't making anything. I don't know.
So your equation will look something like
He probably
that.
does.
Y minus number, you'll have a previous slope. X minus number, the slope they gave you was 1 7. This would be your parallel.
She had to write, please pay attention.
If you want perpendicular, the only difference, flip the 3 over, make it negative. That's the only difference. That's where they go,
Your
that's
response
parallel.
is saying I do not.
It's really simple, to be short.
There's not even a verb. Oh.
I think I'm just gonna sit here for now and just take a break.
Oh man, we can't.
Have you seen Dwight?
I'm making them clean my car.
Someone spilled Dr. Pepper all over me yesterday, Ward.
In my car.
He told me it was on purpose though. He's like, yeah, I might
In my car.
That's kind of mean.
So now my car's stinking. And there's.
And then we said